Unit 9, Lesson 1, Parametric Equations in Calculus. A watermelon is placed on a catapult 5 feet above the ground and is launched at a 30-degree angle with an initial velocity of 40 meters per second. Using g approximately negative 10 meters per second squared, the path of the watermelon travels along a parabolic path modeled by the equation in graph y equals negative x squared over 240 plus x over the square root of 3 plus 5. By using parameters, we can show where the watermelon is located at a specific time using these equations. X of t equals 20t times the square root of 3, and y of t equals negative 5t squared plus 20t plus 5. So basically, at t equals 0, it was 5 feet above the ground, and t equals 1 second, it's here, 2 seconds, it's here, 3 seconds, it's here, 4, or whatever. I think it ends up, that it might be like 1 second it's here, 2 seconds it's here, or something like that. But basically, as your time goes, you can calculate your x and your y. So these equations are related, and I hope that you were able to get an understanding of that through our discussion, our 7 o'clock discussion. So the example number 1, describe the direction and motion of the watermelon at time t equals 2.5. So I wouldn't use this equation if I had t, because it's just in terms of x and y. Okay, so it's just these points, these xy points along here. But if I'm wanting to know after 2.5 seconds where it was, I can do x of 2.5 is going to give me the left or right direction, and y of 2.5 is going to give me the up or down direction. So if I put this 2.5 into 20, I get 20 times 2.5 times square root of 3, which is 50, square root of 3, which is approximately 86.603. That would be meters. And then my y at 2.5 would be my negative 5 times 2.5 squared plus 20 times 2.5 plus 5. And so if I put that in my calculator, I get 23.750 meters. So the watermelon travels 86.603 meters. And we're going to assume that right is positive and up is positive, to the right, and 23.75 meters up. So the direction and motion of the watermelon at time t equals 2.5. So that's the direction and the motion. So it would have gone to the right that many meter, 86.603, and up 23.750. So at 2.5 seconds, it's going to be about right there. Okay. The 86 is your x, and the y is 23. So now, example number 2. For t greater than or equal to 0, a particle is moving in the xy plane, is modeled by the parametric equations x of t equals t cubed minus 3t squared minus 9t, and y of t is t cubed minus 15 halves t squared plus 18t. At what time t is the particle at rest? Remember, at rest means 0 velocity. And these are position equations. They're position in terms of time, but they're still position equations. And so if I want to know when my 0 velocity is, I'm going to take the first derivative of my position equations. Okay, so my first derivative of x prime of t is going to be 3t squared minus 6t minus 9. If I want to know when it has 0 velocity, I'm going to set this equal to 0. I notice that there's a 3 in every single one, so I factor that 3 out, Then I'm going to factor my trinomial. -3 and +1, and then if I solve, t minus 3 equals 0, t equals 3, t plus 1 equals 0, t equals -1. We can't have negative time, I throw that out. And then my y prime of t is going to be 3t squared minus 15t plus 18. I'm going to set that equal to 0. I notice that there's a 3 in every single one, so I factor that out. Now I'm going to factor my trinomial. Be careful because this is positive, so that means we need 2 negatives here to make this last one a positive, because the middle one's negative, so we needed 2 negatives. So -2 and -3, if I multiply, I'll get +6. If I add, I'll get -5. That gives me t equals 2 and t equals 3. We want to notice where they are the same. They both are 0, right? So they at t equals 3, x prime of t and y prime of t are both 0. So we say that x prime of t equals 0 and y prime of t equals 0 at t equals 3 seconds. And so that would be when the particle is at rest. So particle is at rest at t equals 3 seconds. Okay. And now we have officially given the formula here for dy dx. Now, remember, this would be y as a function of x. And we give a way to take those x of t and y of t formulas and make it a dy dx. And this is the formula. You take dy dt and divide it by dx dt. Okay, so that will always give you that dy dx. This dy dx is the slope of the tangent line still, always. So, you know, if you look at dx dt and dy dt, they're not the slope of the tangent line. They are like velocity, they're velocity. So they're telling you the x at a certain time t. You would not get the slope of your tangent line for this, for the function, you know, you're talking about the function y of x. And these are y of t and x of t functions, right, that you're getting these derivatives from. So just so you keep it straight, anytime they ask for the slope of the tangent line or the equation of the tangent line, you're going to be searching for, or you're going to be trying to solve for dy dx, not dy dt or dx dt, but you are going to need them to solve dy dx. So now your second derivative is the derivative. This is like your, you know, the derivative of that derivative you just found, right? So look, d dt of the thing you just found, dy dx, and then divided by dx dt. And then the third derivative is d dt, the derivative of the second derivative, divided by dx dt, right? So remember to divide by dx dt. All right, so a curve C is defined by the parametric equations x equals t squared and y equals t cubed minus 3t. So find dx dt and dy dt. So your dx dt is just 2t, and your dy dt would be 3t squared minus 3. Then it says find dy dx. Well, we know that dy dx is dy dt divided by dx dt. So that's going to be your 3t squared minus 3 over your 2t. So that's your dy dx. And now they're asking for that second derivative. Please be careful on this one because I have to use the quotient rule for the numerator, but my denominator is still just going to be divided by 2t. Because look, I have to divide by that dy, or dx dt. But this one is going to be low d high minus high d low over the square of what's below. But you had to remember to then divide by that dx dt. So this is 12t squared minus 6t squared plus 6 divided by 4t squared, and then instead of division by 2t over 1, we're going to multiply by 1 over 2t. And this is going to give us, we're going to add like terms, 6t squared plus 6 over 8t cubed. And then if I factor a 2 out and factor a 2 out of the denominator, it simplifies to this. So that's your second derivative. Now part D on the next page is still using the same two parts of the curve. So curve C has two tangent lines at the point 3, 0. Now this is an xy point. So your x is 3. Well, that means you're going to take your the x of t equation. I'm just going to rewrite these so that I don't forget what they are. And you're going to say, okay, if this is 3, what is my t? And if you take the square root of both sides, your t is either plus or minus square root of 3. And your y is 0, so you're going to put 0 in for y. And I'm going to go ahead and factor the t out. So we've got t equals 0, we've got t squared equals 3, or t equals plus or minus the square root of 3. So notice that where they are the same is plus or minus square root of 3. And so those are the values that you are going to want to put into your, because you're looking for, it has two tangent lines there. So, you know, you're going to take that square root of 3 and negative square root of 3 and calculate the slope of the tangent line at that point. So I'm going to go ahead and do the positive square root of 3 first. And the slope of our tangent line was this 3t squared minus 3 over 2t. So 3 square root of 3 squared minus 3 over 2 times the square root of 3. This is going to give me 6 over 2 root 3, which gives me 3 over root 3. And if we wanted to rationalize it, we would just rationalize, you know, multiply by square root of 3 over square root of 3. And we would end up, the 3's would end up canceling, and we'd just get root 3. So there's that slope of the tangent line for that t value of positive square root of 3. And now we're going to do the same thing with the negative square root of 3. I just put that negative there like that. And so this ends up giving us, you know, basically the same thing. We're going to end up with 6 over 2 root 3, which is only it's going to be negative 6. So, or, you know, I put that negative on the bottom up. Negative 6 over 2 root 3, and then that gives me negative 3 over root 3, which gives me final answer of negative square root of 3. And they want the equations of these tangent lines, okay? And so one of them has a slope of root 3, and the other one has a slope of negative root 3. And if you want to come find the points, or no, they're both at 3. Even if we put the square root of 3 and the negative square root of 3 back into your equation, you'd get 3, 0. So now our tangent line number 1 is going to be y equals the square root of 3 times x minus 3 and then plus 0. And then tangent line number 2 is going to be y equals negative square root of 3 times x minus 3 plus 0. So there are your equations for your two tangent lines that go through that 3, 0. Okay, and now example number 4, given the parametric equations x equals 2 cosine theta and y equals 3 sine theta, write the rectangular form by eliminating the parameter. So we, when we've got cosine and sine, we're going to divide both sides by the, anything that is being multiplied by the cosine, and then we're going to square both sides. So this is going to be x squared over 4 equals cosine squared theta. And then you're going to do the same thing, divide by 3 on both sides so to isolate that sine, and then square both sides. We're trying to get it into the format where we can put it into a rectangular form. So we want to get rid of those thetas, and we want it to just be y and x. So now, if I take this x squared over 4 equals cosine squared theta, and y squared over 9 equals sine squared theta, and I say I'm going to add those together, I get x squared over 4 plus y squared over 9 equals cosine squared theta plus sine squared theta. And hopefully you remember that that is your Pythagorean identity, and that leaves you with a rectangular form of x squared over 4 plus y squared over 4 equals, or y squared over 9 equals 1. And if we graph this, I hope you remembered that looking at this, this is like x squared over 2 squared plus y squared over 3 squared equals 1. And this is in the format of an ellipse. And this 2 right here says how far away from 0, 0 you are on the x-axis. So I'm 2 this way and 2 that way. And then the 3 here underneath the y squared, the 3 squared, is how far away you are along the y-axis from your 0, 0. And so you can see that this ends up being an elongated ellipse. Didn't draw it very well, but and then they say, find the slope of the curve at theta equals pi over 3. So we would want our dy dx. And what shape did you get? You got an ellipse. You would want your dy dx at theta equals pi over 3. Well, I'm just going to go over here. My dx dt from this equation right here is going to be 2 sine theta. My dy dt from this equation right here is going to be negative, or no, sorry. This one's negative 2 sine theta, sorry. And this one is positive 3 cosine theta. Did you catch me? So our dy dx should have been 3 cosine theta divided by negative 2 sine theta. So if I want that dy dx at pi over 3, I'm going to calculate 3 cosine pi over 3 divided by negative 2 sine of pi over 3. So I'm just going to go ahead and sketch a little 60-degree angle here, because that's what pi over 3 is. So 3 times the cosine would be 3 times 1/2, because adjacent over hypotenuse, and then divided by negative 2 times, and then the sine would be square root of 3 over 2. So this becomes 3/2, and look, the 2's cancel. So division by negative square root of 3 over 1 is multiplication by negative 1 over square root of 3, giving me negative 3 over 2 root 3, which you could say, okay, I quit, that's my answer, or you could rationalize it. If you rationalize it, it simplifies to negative root 3 over 2. So that's the slope of the curve at theta equals pi over 3. Write the equation of the tangent line through this point. Okay, so we have to find that point. X equals 2 cosine pi over 3 would be the x value at that point. Y equals 3 sine of pi over 3. And so x equals 2 times, and then the cosine was 1/2. So our x is 1. And y equals 3 times the sine is square root of 3 over 2. So our y would be 3 root 3 over 2. And so we found our dy dx already, right? This was our dy dx. So if I'm writing the equation of the tangent line, this is my slope, negative square root of 3 over 2 times x minus 1 plus 3 root 3 over 2, because that was my point, my xy point at pi over 3, and this was my slope up here. This was my slope at pi over 3. And these were my, that is my point at x equals pi over 3. Or no, not x, theta. But this is your equation of your tangent line. Okay, example number 5. Find all points, if any, of horizontal and vertical tangency to the curve using a graphing utility to confirm your results. Given your x is equal to t plus 4, that means your dx dt is 1. And your y equals 2 cubed minus 3t. That means your dy dt is 3t squared minus 3. And if I was looking for my dy dx, it would be my dy dt over my dx dt. Okay, so my dy dx is just 3t squared minus 3. And our when we're looking for horizontal tangency, we're looking for where our dy dx equals 0, and our vertical tangency is when our dy dx is undefined. And so I can see I don't have a denominator here, so there's no way for my dy dx to be 0 in the denominator. So dy dx equals undefined, not going to happen, because there is no denominator, okay? So that means that for vertical tangency, we're going to have none. But for horizontal tangency, we're going to set our 3t squared minus 3 equal to 0. 3t squared equals 3. T squared equals 1. T equals plus or minus 1. So those are the two places where you're going to have horizontal tangency. So if I put my t equals 1 in, I get 1 plus 4 for x, so my x is 5. And my y would be 1 cubed minus 3 times 1, so that would be negative 2. So that's the point 5 comma negative 2 xy. That's when t equals 1. And when t equals negative 1, my x is equal to negative 1 plus 4, so x is equal to 3. My y is equal to negative 1 cubed minus 3 times negative 1, so that's negative 1 plus 3, which is 2. So that's the point 3 comma 2. So I said vertical none, horizontal would be at the point 5 comma negative 2 and 3 comma 2. So that's where your horizontal tangents are. And there were no vertical tangents. Okay, and the last example in number 6, determine the t intervals on which the curve is concave up or concave down. And here's my curve. X equals sine t, y equals cosine t. So my dx dt is cosine t. Y equals cosine t. My dy dt is negative sine t. So my dy dx is my dy dt divided by my dx dt, which is actually negative tangent t. And then if I wanted to find concavity intervals, I should be thinking of the second derivative. So I just took the first derivative. Now I need to find that second derivative. So that's going to be the derivative of negative tangent t, which is negative secant squared t, divided by dx dt. So there's two ways you could simplify this. You could make it negative secant cubed t, or you could make it negative 1 over cosine cubed t. Okay, so either one of these, I don't care which one, but you're going to take that second derivative, and I guess I'm going to choose this one. And you're looking for where is it 0 and where is it undefined. Okay, so I'll say is never 0, right? Because whatever makes your numerator 0 would make it 0, and -1 will never be 0. Okay, if I want to see what makes it undefined, I'd be looking at what makes that 0. And I know that, you know, you're just basically looking for what values of t is the cosine 0. And that would be, and remember, you're in this interval from 0 to pi. So that's just in the first and second quadrants. The only time my cosine is t is when t is pi over 2. Okay? And so that's going to be what you're looking at as your critical point. And remember, you're going from 0 to pi. So I just decided to put in pi over 4 because it's halfway, just to see what my second derivative sign was at, you know, in between 0 and pi over 2. And so if I put a pi over 4 in, I know that the cosine of pi over 4 is positive, but then you've got that negative up there, -1 divided by the, you know, the positive cosine t cubed. So you're going to get a negative. And then thinking about putting any angle, you could use 3 pi over 4 if you wanted to, but cosine is always positive in this second quadrant. I'm sorry, cosine is always negative in this second quadrant. So when you take negative divided by negative, you're going to get a positive for that. So the second derivative is positive in between pi over 2 and pi. So we know that our signs of our second derivative tell us concavity. We know that it's concave up from pi over 2 to pi, and that it is concave down from 0 to pi over 2. Okay, so those are your concavity intervals, and that is the end of